In this video, I'll be giving you some tips for solving the ALEKS problem called Setting Up the Math for a Two-Step Quantitative Problem. There are a lot of different variations of this problem, and I'm definitely not going to be able to show all of them to you, but I am going to solve this one, and I'm also going to kind of walk through the process of one of the other versions of this problem, and hopefully that's enough to get you through whatever you're dealing with. Now, for this problem, two-step quantitative problem, there are going to be two conversion factors embedded in the problem itself, and your first job is to find those two conversion factors. This problem is actually, I think, the trickiest one that I've seen, so it's kind of nice that I'm doing it with you. If you have this one, that's really good because the other ones are quite a bit simpler. So one of the conversion factors embedded in this particular problem is right here, and that is like not super intuitive that that's a conversion factor. The other conversion factor is in this place right there. Now, the other versions of this problem that I've seen, the conversion factors are a lot more obvious than this one. And I'm going to take that information and I'm going to write them in the style of a conversion factor. So the first one, it says 3.00 joules of heat for every 1 degree Celsius. And the second conversion factor is 4.52 joules for every 1 degree Celsius. Now right there, that's kind of a problem for me because those two conversion factors have the exact same unit, and I can see myself getting really confused by the similarity of those two conversion factors. So here's what I'm going to do to try to make it easier for myself. The first conversion factor that I wrote was describing object A. So I'm just going to put a little subscript A next to both of those units so that I know that this conversion factor applies to A. And I'm going to do the same thing for this guy as well. And the other versions of the problem, like I said, are not going to be this tricky. And so these are my two conversion factors. And then, in addition to two conversion factors, there's going to be at least one more piece of important information, one more piece numerical data. And for mine, it's this information right here. I'm going to erase those circles. Object A is seen to cool down by 13 degrees Celsius. So object A has a temperature change of 13 degrees Celsius. It loses 13 degrees of its temperature. It wants us to calculate the rise in temperature of B. So I'm just going to put a little subscript A next to that Celsius assigned to help us keep track of the temperatures. And then what we're trying to figure out is what is the new temperature in B for object B. Now, keep in mind that it does not want us to actually do any of this math. It just wants us to write out a math expression. So, okay, that's all we have to do. It's still pretty tricky. What I do know, another thing I do know about this problem, and this is also another thing that makes this particular version of the problem tricky. You may not have come to this information yet in your chemistry class, but all of the heat that is lost by object A, the hotter one, all of the heat that's lost by object A is absorbed by object B. So all of the heat lost by A is the same as all of the heat that is gained by object B. And this heat is measured in units of joules, not in Celsius. So Celsius is temperature, not the same as heat. So all of the heat in units of joules that's lost by object A is equal to all of the heat in units of joules gained by object B. And again, this is why I think this problem has the potential to be super tricky, because chances are good you haven't talked about this concept yet in class, so you may not know that. The other versions of this problem, like I said, they are quite a bit easier than this one. Okay, so here's what we're going to do. We're going to start by taking the amount of heat that has been lost by object A, that is 13.0 degrees Celsius, object A, and what I'm going to do is figure out how many joules that is, because all of the joules that's lost by A are going to be gained by B. So I'm going to use this conversion factor here to convert from the degrees Celsius of A into joules of A. Multiply by a conversion factor. I want degrees Celsius on the bottom. I want joules on top. My conversion factor says there are 3 joules for every 1 degree Celsius. That's going to cancel out that unit, and I am left in units of joules of object A. Whatever that is, I guess I need one more conversion factor. I guess I'm going to write a conversion factor up here. From this information, I can say that the joules of A are equal to the joules of B, and that allows me to write a conversion factor that looks like this: joules of A over joules of B, or a flip-flop, joules of B over joules of A. So what I'm ultimately trying to do is figure out the degrees Celsius for object B, which is located right here. So I need to get from joules of A into joules of B. This is the conversion factor that I'm going to use for that. Next step in this process, joules of A convert into joules of B, and that is a 1-to-1 conversion. Joules of A are equal to joules of B. So this is going to cancel out the joules of A. In my last step, I'm going to use this conversion factor to go from joules of B into degrees Celsius. I want joules of B on the bottom. I want degrees Celsius of B up on top. And I'm going to use this as a conversion factor, but recognize that the units are in the wrong place for this conversion factor, the way that it's written right here. That's okay. Conversion factors can always be flipped upside down as needed. So that's what I need to do with this one. I need to turn it upside down so that I have my units in the correct spot so that they're going to cancel out appropriately, like that. And all of this is what we would enter in the box as the solution to this problem. Of course, we don't want the little blue lines on there, so you're going to need to get rid of those because we're not showing the cancellation of the units. And also, for this version of the problem, like I can't actually see, oh, there are degree symbols. Yeah, so you are going to have the degree symbols in there. For this ALEKS problem, I really don't think that the subscripts are supposed to be there. Like, I don't think that I think you're going to want to take those out. And you may not want this term in there either. Probably won't. At this, like I said, this is a particularly tricky version of the problem. Let me describe an easier version of this problem. I'm just going to kind of draw a line, separate. So on another screen, I'm looking at an easier version of the problem. The easier version of the problem is talking about an airplane, a military jet, and it's saying that this military jet burns 1,800 kilometers per hour of fuel at a rate of 73.4 liters per minute. And it wants to know how much fuel, so that would be in liters, how much fuel would be consumed on an 800 kilometer trip. And so right off the bat, like, this problem is quite a bit easier than the one that we just did up here. Remember I told you that these problems are all going to have two conversion factors? Well, in this version of the problem, the military jet problem, the conversion factors are super easy to find. Like, they're just written like normal conversion factors. And it's really clear about what we need to calculate and what we're starting with and our pathway to get from liters or from kilometers to liters. We don't have any situation like this where the same unit is being used in both conversion factors, and there aren't any concepts that you would need to know that you maybe haven't covered yet in class. So this version of the problem and the other versions are much more straightforward. For the problem in this format, we're going to start by writing the number, not the conversion factors, but start with the number that has been given to you by the problem. So that's 800 kilometers. Now you're going to find your conversion factor, look at your two conversion factors, find the one that involves that kilometer unit. That's what we're going to use next. Keep in mind, it is possible there might be slight unit incompatibility, like perhaps I had been given 800 meters as my starting point. And then I would need to recognize that I'm going to have to convert the 800 meters into kilometers in order to make this conversion factor work. But that's stuff you know how to do. All right, so here's my first conversion factor that I need to apply. I'm going to set this up like a more traditional format. I want my kilometer unit on the bottom because I want to cancel that out. And this conversion factor is going to let me convert into hours like that. Notice that this conversion factor is not in the right order that I need it. I need hours on the top, and in the conversion factor that I have, they're down on the bottom. But remember, we can flip-flop conversion factors. So we're just going to turn this conversion factor upside down. 1 hour, 1,800 kilometers. and those kilometer units are going to cancel out. Now we're needing to use the next conversion factor, which is units of liters per minute. Here's a little bit of unit incompatibility. I've got hours. I need minutes in order to be able to use this conversion factor. No problem. We know how to convert from hours to minutes. Hours goes on the bottom. Minutes goes up on top. Kind of bugs me that I wrote it that way. I think little m means meters. Okay, so from hours to minutes, we know that 1 hour is 60 minutes, and there's that conversion. And now we are ready for the last conversion factor. We want minutes down on the bottom, and we want liters up on top. That is the format that this conversion factor is in, so we don't need to do any flip-flopping. 73.4 liters per minute. Keep in mind again that ALEKS is not asking you to do the math on this. It just wants you to set that problem up, including units.